Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers section 5.1 on eigenvectors and eigenvalues. I'll go over all of the topics listed here, provide you with steps to solve these types of problems, and walk through lots of example problems. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. Let's begin by talking about the connection between eigenvectors, eigenvalues, and linear transformations. Eigenvectors and eigenvalues are fundamental concepts in linear algebra that provide crucial insights into the behavior of linear transformations. A linear transformation is often written as T of x is equal to A times x, where multiplying a vector x by a matrix A transforms vector x into a vector T of x. This matrix A has eigenvectors and eigenvalues associated with it. Eigenvectors and eigenvalues are used to identify invariant directions where vectors maintain their alignment, understand how these directions are scaled, reflected, and rotated, simplify the transformation through diagonalization for further analysis, and then predict behavior of dynamical systems, including long-term behavior. Let's now look at some transformations AX1, AX2, and AX3 and see how their lengths and directions compare to X1, X2, and X3. We'll begin by multiplying matrix A by vectors X1, X2, and X3. AX1 is the matrix 1, 2, 1, 0 times the vector 1, 1, and that gives us the vector 2, 2. AX2 is our same matrix A times vector x2, which is 1 minus 1, and this gives us the vector 0, 2. AX3 is our same matrix A times vector x3, which is minus 1, 2, and this gives us the vector 1, minus 2. In the graph below, I've plotted x1 and ax1, x2 and ax2, and then x3 and ax3. Notice that ax1 and x1 have different lengths, but the same direction. If we look at the values of the vectors ax1 and x1 above, we can see that ax1 is equal to 2 times x1, and so it's a multiple of x1. If we look at ax2 and x2, we notice that they have different lengths and different directions. Because of this, ax2 is not a multiple of x2. Lastly, if we look at ax3 and x3, we notice that they have the same length but opposite direction. We can write ax3 is equal to minus 1 times x3. Since ax1 is a multiple of x1 and ax3 is a multiple of x3, vectors x1 and x3 are called eigenvectors of matrix A, and their corresponding eigenvalues are 2 and minus 1. Now that we have an intuitive sense of what an eigenvector is, let's see how eigenvectors are formally defined. An eigenvector is defined as a non-zero vector that remains aligned with itself under a linear transformation. That means that multiplication by A does not alter its direction. Eigenvectors and eigenvalues are defined only for square matrices because the concept involves multiplying a vector by a matrix and obtaining a scaled version of the original vector. Vector x is defined to be an eigenvector of matrix A if A times x is equal to lambda x for some scalar lambda. That scalar lambda is then called the eigenvalue of matrix A. I want to now use this definition to show you why an eigenvector is defined to be a non-zero vector. If we allow x to be the zero vector, this equation becomes A times 0 is equal to lambda times 0. This equation is going to be satisfied for any value of lambda, so we say that lambda can be any number. Because of this, x is equal to 0 would not provide any meaningful information about the behavior of A, and that's why an eigenvector is defined to be a non-zero vector. Let's now talk about eigenvalues. An eigenvalue associated with a given eigenvector tells us how much a linear transformation scales an eigenvector. An eigenvalue is the scalar lambda in this equation. If the absolute value of lambda is greater than 1, then our eigenvector x is stretched. If it's less than 1, then our eigenvector is compressed. If lambda equals 1, our eigenvector remains unchanged. And then if lambda is negative, our eigenvector reverses direction. I also want to note that if lambda is a complex number, our eigenvector is rotated and scaled. For now, we're only going to be working with real eigenvalues. Let's now talk about how to determine if a given vector is an eigenvector of a matrix. If x is an eigenvector of matrix A, we say that A times x is equal to lambda times x. To determine if a given vector is an eigenvector of a matrix, there are two steps that we can follow. The first step is to find A times x, and then the second step is to check if A times x is a multiple of x. If it is a multiple, then we say that x is an eigenvector and lambda is the corresponding eigenvalue. If ax is not a multiple of x, then x is not an eigenvector. Let's now walk through two example problems where we're asked to determine if x is an eigenvector of matrix A. If it is, we want to find the eigenvalue. Our first step is to compute A times vector x. Our matrix A is 3, 8, 0, minus 1, and we multiply it by our vector x, 1, 2, and this gives us the vector 3, 6. Our second step is to see if this vector that we just computed is a multiple of x. We have vector 3, 6, and we want to see if it's a multiple of vector 1, 2. We can see that if we multiply vector 1, 2 by 3, that we get vector 3, 6. So vector 1, 2 is a multiple of vector 3, 6. This tells us that x is an eigenvector of matrix A, and that the eigenvalue is this value equal to 3. Let's now look at our second example. You might want to stop the video and work this example on your own. Just like in our first example, we'll take matrix A and we'll multiply it by our vector x. What we get is the vector 9 and then 23. We'll then check if our vector 9, 23 is a multiple of 3, 1. There's no number that we can multiply vector 3, 1 by to get vector 9, 23, so we say that these two vectors are not multiples of each other. And that tells us that x is not an eigenvector. Let's now talk about how to determine if a given number is an eigenvalue of a matrix. Lambda will be an eigenvalue of matrix A if ax is equal to lambda x has a non-trivial solution, meaning x is not equal to 0. I'm now going to go over two ways that we can determine if ax is equal to lambda x has a non-trivial solution. If we rewrite this equation as ax minus lambda x is equal to 0, and then factor out a vector x, we get this equation. If we let a matrix B equal A minus lambda I, we can see that this equation is just B times X is equal to 0. We've actually already worked with this equation quite a bit. The equation Bx is equal to 0 has two types of solutions. One solution is when X is equal to 0, and then the other solution is when X is equal to 0 and infinitely many X is not equal to 0. When X is equal to 0, every column in matrix B has a pivot, and our determinant B is not equal to 0. If we have non-trivial solutions in addition to x is equal to 0, then there must be a column in matrix B without a pivot. In other words, there must be a free variable in matrix B. When we have a column without a pivot, our determinant is equal to 0. We can use this theory to write down two different ways to determine if a given number lambda is an eigenvalue of a matrix. In the first method, what we'll do is we'll take A minus lambda I and we'll augment it with 0, put it in echelon form, and then see if it has a free variable. If it has a free variable, then lambda is an eigenvalue, and if it doesn't have a free variable, then we know that lambda is not an eigenvalue. The second method that we can use is to compute the determinant of A minus lambda I. If our determinant is equal to 0, lambda is an eigenvalue, and if our determinant is not equal to 0, then we know that lambda is not an eigenvalue. Let's now walk through an example to see how this works in practice. We're given a matrix A and an eigenvalue equal to 2. I'll show you how to use both ways to work this problem. The first way is to augment A minus lambda I with 0 and then put it in echelon form. Let's first compute A minus lambda I. Since we haven't done this before, I'm going to work this out in detail. And once you do it once, you'll know exactly what to do. Here's our matrix A, and we're going to subtract lambda times our identity matrix. This gives us the matrix minus 3 minus lambda, 6 minus 5, and then 8 minus lambda. You can see that the lambda gets subtracted from the entries along the main diagonal. Let's now augment this with 0. We'll write down A minus, and then instead of lambda, let's plug in exactly what lambda is. Lambda is 2, so we have A minus 2i, and we're going to augment this with 0. So let's go over here to the matrix that we already computed, and let's substitute in that lambda is equal to 2. This gives us a minus 5, 6, and then a minus 5 and another 6. And that's augmented with 0. We only have to do one step to put this in echelon form. We'll just multiply row 1 by minus 1 and add it to row 2. This gives us minus 5, 6, and then 0, 0. Because our second column is missing a pivot, x2 is going to be a free variable, and ax is equal to lambda x is going to have a non-trivial solution. This tells us that lambda is equal to 2 is an eigenvalue. Let's now look at the second way to do this problem. For this method, we need to compute the determinant of A minus lambda I. This is the determinant of minus 3 minus lambda, 6 minus 5, and then 8 minus lambda. We'll then plug in lambda is equal to 2, and we get minus 5, 6, minus 5, 6. And that determinant is equal to 0. A value of 0 for the determinant tells us that a column of A minus lambda I is missing a pivot, and AX is equal to lambda X has a non-trivial solution, and then lambda is equal to 2 is an eigenvalue. The next topic that we're going to talk about is how to find a basis for an eigenspace corresponding to a given eigenvalue. Recall that the null space of a matrix A is all solutions X to A times X is equal to 0. Just like the null space, the eigenspace of a matrix A corresponding to an eigenvalue lambda is all solutions X to the equation A minus lambda I times X is equal to 0. This is often called the null space of A minus lambda I. The eigenspace of a matrix A contains the 0 vector, and it also contains all the eigenvectors corresponding to the eigenvalue lambda. Just like with a null space, the number of vectors in an eigenspace equals the number of free variables in A minus lambda I. To find the basis for an eigenspace corresponding to an eigenvalue, there are 3 steps that we need to complete. The first step is to augment a minus lambda I with 0 and put it in reduced echelon form. Notice that this is reduced echelon form and not echelon form because we actually have to find the solution x. Our second step is to write the solution x in parametric vector form. And then our last step is to form the basis from the vectors in the solution that we found for x. We'll now walk through two examples where we'll find a basis for the eigenspace corresponding to the listed eigenvalue. In our first example, we have a 2 by 2 matrix, and in our second example, we have a 3 by 3 matrix. Let's start by looking at our first example. Our first step is to take a minus lambda I, augment it with 0, and put it in reduced echelon form. A minus lambda I is going to be 3 minus 2, 6, minus 5, and then 8 minus 2, and we'll augment that with 0. This is equal to minus 5, 6, minus 5, 6. Because our second row is a duplicate of the first row, we know that row is going to go to 0. And then we can just take our first row and divide it by minus 5. This gives us the matrix 1 minus 6/5 augmented with 0, and then the second row is a row of zeros. Our second step is to find a solution for x in parametric vector form. If we look back to step 1, we can see that x1 is going to be equal to 6/5 x2, and that x2 is a free variable. Our vector x is equal to the vector x1, x2, and we can just plug in what we got. So x1 is 6/5 x2, and our free variable goes in as itself. We can then take the free variable out in front, and we're left with the vector 6/5 1. In step 3, we'll form the basis by choosing a value for our free variable x2. Because of the 6/5 in our first row, I'm going to choose x2 to be equal to 5 so that our basis won't have any fractions in it. Our basis contains the vector 6, 5. That's just substituting in that x2 is equal to 5. Let's now look at our second example where we have a 3 by 3 matrix. We're going to follow the same steps that we just did in our first example. We're going to take a minus lambda I, and we're going to augment it with 0. This is going to give us 6 minus lambda minus 2, 2, 0, 4 minus lambda, 0, and then 3 minus 3 and 7 minus lambda, and we'll augment that with 0. Let's now plug in that lambda is equal to 4. This gives us 2 minus 2, 2, 0, 0, 0, 3 minus 3, and then 3. You can see that rows 2 and 3 are multiples of row 1, so those rows are going to go to 0. So we're really just going to have to do one step in our reduction. And what we'll do is we'll take the first row and we'll divide it by 2. This gives us 1, 0, 3 halves, augment it with 0, and then our last two rows just contain zeros. Our second step is to find our solution x. We see from step 1 that x1 is equal to minus 3 halves x3. x2 is a free variable, and x3 is a free variable. This gives us the solution x is equal to x1, x2, and x3. And now we just plug in what we got. x1 is minus 3 halves x3. x2 is a free variable, so it goes in as itself. And then x3 also goes in as itself. We now need to split our vector apart. And to do that, let's write our second entry as 1x2 plus 0x3, and then our third entry as 0x2 plus 1x3. That'll just help when we split it apart. We'll first pull out an x2, and we have a 0, a 1, and a 0. And then we pull out an x3, and we have a minus 3 halves, a 0, and a 1. Now all we have to do is find a value for x2 and x3 and write down our basis. I'm going to choose x2 to be equal to 1, and then I'm going to choose x3 to be equal to 2 to get rid of our fraction. You could have also let it be equal to minus 2 if the first entry you wanted to be positive instead of negative. Our basis then contains these two vectors. The first vector is 0, 1, 0, and our second vector is minus 3, 0, and 2. We can also talk about the geometric description of this solution. It contains two vectors, so our geometric description is going to be a plane in R3. The last topic that we'll talk about is eigenvalues of triangular matrices. In the video for section 2.3, we looked at three types of triangular matrices: upper triangular, lower triangular, and diagonal matrices. I'm going to work with an upper triangular matrix to show you how to find the eigenvalues of a triangular matrix. We know that A times X is equal to lambda X will have a non-trivial solution X, and lambda will be an eigenvalue of A if the determinant of A minus lambda I is equal to 0. The determinant of A minus lambda I is written here, and because it's a triangular matrix, it's equal to the product of the entries along its main diagonal. That's given right here. Lambda is going to be an eigenvalue if this determinant is set equal to 0. When we do that, we get that lambda is A11, A22, and A33. Notice when we go back to matrix A that those are just the entries along the main diagonal. We can now state that the eigenvalues of a triangular matrix are the entries along its main diagonal. Let's now look at two examples where we're going to find the eigenvalues of the following matrices. The hardest part of this problem is realizing that the matrix that you're given is a triangular matrix. Once you realize that, you can just write down the eigenvalues. In our first example, we have a lower triangular matrix and these entries along the main diagonal. This tells us that lambda is equal to 1 and 3. Because there are two values of 3, we'll often say that 3 has a multiplicity of 2. In our second example, these are the entries along our main diagonal, so we just say that lambda is equal to 0, 2, and 3. Note that an eigenvalue can be equal to 0, and we'll talk more about that in the next video, but an eigenvector cannot be equal to 0. Be sure to check out the next video in this series where I'll teach you all about characteristic polynomials and the characteristic equation.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.